Hi everyone, I am Vignash, currently working as an assistant professor in the Department of Civil Engineering, St. Peter's Engineering College. In this lecture, I am going to discuss about analysis of determinate plane trusses. Analysis of determinate plane trusses. So basically this topic is from the subject structural analysis of civil engineering. So let us see what is analysis and then what is a determinate plane truss. So as the subject itself says structural analysis. Let us see what is analysis first. Let us see what is analysis first. Analysis means calculation of unknown forces. So analysis means calculation of unknown forces. Now when we come to calculation of unknown forces, the unknown forces may be of two types. One is external support reactions and the unknown forces may be internal member forces. So analysis means analysis of structure means we analyze the structure, means calculation of unknown forces that are present in the structure, maybe a beam, maybe a frame, like that. So next, determinate. So let us say we have a structure. Now what is a determinate structure? Determinate structure means if we have a structure, it will have some unknown forces. Let us say the total number of unknown forces x. Now we analyze these structures by the use of equilibrium equations. So if we are able to analyze the structure with the help of only equilibrium equations, then the structure is called determinate structure. Now in simple we say, if the number of unknown forces and the number of available equilibrium equations are equal, then the structure is called a determinate structure. So unknown forces is equals to the equilibrium equations, where y is number of available equilibrium equations, where x is unknown forces. So if the number of unknown forces is equals to the number of available equilibrium equations, then that structure is called a determinate structure. Now let us see what is a plane truss. Now let us see what is a plane truss. Now till now I have been using the word structure, structure, structure. Now let us see what is a structure first. What is a structure? Structure. A structure is a stable system which, when loaded, it will get deformed, and once if the load is being removed, it will regains its original position. So basically structure is a stable system comma deforms under the application of external load. And the main thing that is regains its original position or shape once the external load is removed. Once the external load is removed. So basically a structure means it is a stable system which undergoes deformation when it is loaded externally, and the main thing is it should regain its original position once the external load is removed. Such a system we call a structure. Now we have different types of structures. So we have mainly three different types of structures. First one is a skeletal structure. Skeletal structure. Second one is a surface structure. And the third one is a solid structure. Now let us understand what is a skeletal structure. Now a skeletal structure is the one in which any one dimension of the member is predominant. Let us say any one dimension is predominant. Predominant. What do we mean by that? It means, let us take a beam. If we consider a beam, when compared to the length of the beam, the cross sectional dimensions, that is width and thickness, are very less. It means the length is predominant here. So such things we call as skeletal structures. Similarly, a surface structure means any two dimensions are predominant. So let us take the example of a slab. In a slab, for a slab, the length and width are predominant when compared to the thickness of the slab. So such kind of structures we call surface structures. Then coming to the third, solid structure, all the three dimensions are predominant, means all the three dimensions are considerable. Let us take the example of a massive foundation. So all three dimensions are predominant. So if you take the examples here, framed structures, then if we take the example here, so we can take a slab. If we take the example here, we can take the example of a massive foundation. Where all the three dimensions are predominant. Now again, if we see a skeletal structure, this is again classified based on the type of the joint. It is classified based on the type of joint. So let us take a framed structure, something like this. So if you observe, these are a beam, this is a beam, this is a column. These two are skeletal structures because only one dimension is predominant. So combination of all these beams and columns, we get a skeletal structure, something like this, like a frame. So based on the type of joint, so if you are joining all these skeletal structures together, we need a joint. So based on the type of this joint, it can be classified as two things. One is a pin jointed frame, the other is a rigid jointed frame. Now, as I said, based on these joints, the skeletal structure are divided or classified into two things. One is a pin jointed frame and the other is a rigid jointed frame. Now, let us see what is a pin joint and what is a rigid joint. Pin joint means it offers resistance to only translation. Now, what is a translation? Translation means movement in horizontal direction and vertical direction. Let us say x and y. Translation means movement in horizontal direction and vertical direction. So a pin joint offers resistance to only translation, but it doesn't offer any resistance to rotation. So when it is when a movement is being applied on it, it will not resist that movement. So it will resist only translation, and then a rigid joint is the one in which it resists both the translation and the rotation. So it will resist both. So rigid joint both the translation and rotation. Restricted. Here only translation is restricted, or sometimes we can call it as resistance restrainment also. So a skeletal structure is again classified based on based on type of joint. One is pin joint and the other is rigid joint. So we'll have pin jointed frame and a rigid jointed frame. Now let us see what is a truss. So here we are, truss. So truss is basically a skeletal structure and it is a pin jointed structure. So if the structure is having pin joint, then it is called a truss. So, and what is a plain truss? If all the joints of the truss are only in one plane, one single plane, then it is called a plain truss. Now we'll have sometimes this is also called as 2D trusses in short, because only we are dealing with a single plane. Again plane space trusses also we can say. Space trusses means the joint or the members of the truss may be in more than one plane. So in that case those trusses are called space trusses. So right now we are dealing about an plane trusses. So let us see once recap what we have discussed up to here. So we are discussing the topic analysis of determinate trusses, plane trusses. So analysis means calculation of unknown forces. The unknown forces are maybe external support reactions and internal member forces. Then determinate structure. A determinate structure is the one in which if you are able to calculate all the unknown forces with the help of equilibrium equations alone, then it is called a determinate structure. Now a plane truss, it is a skeletal structure. It is a two-dimensional structure. Plane means it is a two-dimensional structure where all the members are present in only one plane, a single plane. Again, and the joints are pin joints. So basically a truss is a pin jointed frame. In short, we can say the truss is a pin jointed frame. So we are doing the analysis of determinate pin jointed plane trusses. So in simple, we are doing the analysis of pin jointed determinate plane frames. So next we have discussed what is a structure, then what are the different types of structures. So basically a structure is a stable system which undergoes deformation when it is loaded and again regains its original shape or position once the load is removed. So structures are classified in three things. One is skeletal structure, surface structure, solid structure. So in the skeletal structure, one dimension is predominant, and in the surface structure, two dimensions are predominant, and the solid structure, three dimensions are predominant. Example we have taken as a beam or a column. For a surface structure, we have taken a slab, and for a solid structure, we have taken the example of a massive foundation. Okay. Oh. So we have seen the introduction. Now let us see what are the prerequisites to understand this concept. So you need to have the basic knowledge of equilibrium conditions, support reactions, application of the concept of free body diagram. So these are the prerequisites that are required to understand this concept. So equilibrium conditions. So what are equilibrium conditions? Now let us say any body is said to be in equilibrium if the net acceleration of the body is 0. Net acceleration of the body is 0. Net acceleration of the body is 0. So and if the net acceleration is 0, then we know that F is equals to ma. If acceleration is 0, then F equals to 0. So let us say if this is sigma forces sigma A. So there may be multiple number of forces acting on a single body. So in that case, if you take the summation of all the forces, then it is 0. Again, if the summation is 0. So if the net this is linear acceleration. Also, if we say it should for the body to be in equilibrium, so angular acceleration should also be 0. It means there should be it should be the rotation should be restrained. Means so moment is also 0. So sigma m is equals to 0. So these are the basic conditions for equilibrium. So I have touched upon very briefly. This will be in detail will be dealt in engineering mechanics. So there we'll see it in detail. Then again support reactions. So we'll have different types of support reactions: a roller support, a hinge support, a fixed support, a fixed support. All these things are there. There are some other support reactions also. So we should be able to understand the support reactions also. So when I am dealing the problem, we'll see the support reactions. Then again application of the concept of the free body diagram. Now I'll discuss about the free body diagram in simple. So what is a free body diagram? A free body diagram is a diagram which represents the forces acting on the body. So a free body diagram is the diagram which represents the forces acting on the body. Forces acting on the body. So this is very important. In a free body diagram, we represent the forces that are acting on the body. This is very important. So why it is important? When I am dealing the problem, I'll discuss. So now let us go to the analysis part. Analysis part. So to analyze a pin jointed plane frames, that is a plane truss. So analysis of pin jointed plane frames. This is nothing but plane truss. In simple, we can say plane truss. Okay. So to analyze, we have different methods. So first method is method of joints, and we have another method of sections. These are the main things. These are the major methods. In addition to these things, we have another method called tension coefficient method. Tension coefficient method, and the other is a graphical method. So in this lecture, I am going to cover the method of joints. In this lecture, I am going to cover, we'll be discussing method of joints. Before going into the analysis, we'll have some assumptions while doing this analysis. So assumptions in the analysis of plane trusses. So first assumption is load. The first assumption is load acts only at the joints. First assumption is load acts only at the joints. Load acts only at the joints. The second assumption is self weight of the members of the truss is neglected. The second assumption is self weight of the members of the truss is neglected. So self weight is neglected. Self weight is neglected. Now let us understand why these assumptions are made. So load acts only at the joints. When the load is acting only at the joint, it means load. Let us reframe this a little bit, and not on members. So there is no load that is acting on the members. So when the load is not acting on the members, there is no question of shear and bending. So, and again, self weight is neglected. It means where the self weight acts on the member at the centroid. So this is nothing but a simple version of this. So self weight is neglected and load acts only at the joints, means so there is no transverse load acting on the members. So which results in no shear force and no bending moment, and hence only axial forces or load, axial load acts on the members of the truss. So the major assumptions is load acts only at the joints but not on the members, and the second one is we are neglecting the self weight of the members of the truss. So when we are neglecting the self weight, basically the self weight acts, let us say this is a member of a truss. So we assume that the self weight acts at the centroid, that is midpoint here. So if load acts here at the between, so a load is acting on the member if we don't neglect the self weight. So when the load is acting on the member, it is a transverse load which causes shear and bending. So to make analysis easy, we assume self weight is neglected and load is acting only at the joints. So and hence, because of these two assumptions, the third assumption, only axial forces acts on the members. So now we are good to go and see the procedure of method of joints. So I'll take a simple truss problem and see the analysis and find the unknown forces, the support reactions and the member forces. I have already discussed that the unknown forces means the support reactions and the member forces. So let us take a simple truss problem and see the method of joints. Here the diagram is not drawn to scale. Okay, this is a simple truss. If you observe, all the members are in a single plane, so it is a plane truss. Now if you observe, the joints are pin jointed, so it is a plane truss and it is a pin jointed frame. So it is a pin jointed frame and it is a plane frame because all the members are in a single frame, single plane. No, let us see. So if you see, what is the topic? Determinate analysis of what is the topic? Analysis of determinate pin jointed plane frames. A pin jointed plane frame is nothing but a plane truss. So a pin jointed frame is nothing but a truss. A pin jointed plane frame is nothing but a plane truss. So let us see whether it is a determinate structure or not. So what I have mentioned, a determinate structure is the one in which the number of unknown forces is equal to the number of equilibrium equations. In short, if we are able to analyze the structure with the help of equilibrium equations alone, that is, if we are able to calculate all the unknown forces with the help of equilibrium equations alone, then the structure is called a determinate structure. So here the structure is a truss. So let us see the total number of unknown forces here. So as we have discussed, the members carry only axial force. So it means each member will carry only one internal force. So each member will have one unknown force and the support reactions. So if you draw the support reactions, there is a pin joint or hinge joint. So it will have two reactions. One is in the vertical direction and the other is in the horizontal directions. So let us say this is VA and this is HA. And we have a roller support here. It will have only one reaction, that is in the vertical direction. So let us say it as V. So we have, let us calculate the total number of unknown forces. So we have one unknown force here, 2, 3, and in each member we have one unknown force. Let us calculate total number of members. Then total number of members into 1 equals to total internal reactions. So this is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. So we have 7 members, means 7 number of internal forces, and we have 3 external support reactions. So total we have 10 unknown forces. Now see, I have already discussed we need the application of equilibrium. So at each joint, as I have already discussed, this joint doesn't offer any resistance to movement. So it offers only resistance to translation, means at each joint we have only two equilibrium equations, that is sigma fx equals to 0 and sigma fy equals to 0. So at each joint we will have two number of equilibrium equations. So total we have 1, 2, 3, 4 and 5. So 5 into 2 equilibrium equations, 10. So total number of available equations is equals to the total number of unknown forces. So this is a determinate structure. So determinate structure, it is a pin jointed plane frame. So now we start the analysis, that is calculation of unknown forces. I am drawing the free body diagram of the truss. Okay. So in method of joints, what do we do is, so actually we have two equilibrium equations at a single joint. So if you have more than two unknowns at any joint, so we will not be able to calculate the member forces there. So what do we do is, in this analysis, what do we do is, we will select a joint such a way that where only two unknowns are present. We select a joint in such a way that only two number of unknown forces are present, and then we proceed by applying the equilibrium equations. Let us see first this joint. So we have 1, 2, 3, 4, two support reactions. So if we look at this joint, we have one unknown force here, one unknown force here, and one unknown force here. Three unknown forces are present. So we will not be able to analyze. Again, if we see here, 1, 2, 3. Three unknown forces at this joint also. So we'll not be able to calculate the member forces. If we again see here, we'll have 1, 2, 3, three unknown forces. This load P, it is in kilonewton. This is an external load. So this is not an unknown. It will be its value will be given. So for now you understand, you assume that its value is P kilonewton. So again here we have three unknown forces. So it is not easy to calculate the number of unknown forces, value of the unknown forces. So first what we have to do is we have to calculate first these external support reactions. So how do we calculate the external support reactions? By applying the equilibrium equations. So I have mentioned that the joint will not offer resistance to movement, that is rotation. So that is why we will have only two equilibrium equations at each joint. But the structure as a whole offers a resistance to the movement also. That is why as a whole, when we are considering the structure, we will have three equilibrium equations. One is summation of forces in x direction is 0. The other is summation of forces in y direction is 0. And since the structure offers resistance to movement also, the summation of forces since the structure offers a resistance to movement also, the summation of movement in z direction about any point in the plane of truss is equals to 0. Now what is this z and what is about any point in plane of truss? So when we are taking the reference as this is x direction and this is y direction. So when this is x and this is y, the moment this plane will tend to rotate about a direction perpendicular to this plane. This truss is in this plane xy. So if the rotation at all acts, this truss will tend to rotate in a direction perpendicular to the plane of this board. So that is z direction. That is why we take summation of moments about z direction at any point in this plane. So we should not be sticking to that moment at this point is 0, moment at this point is 0. Not like that. So we can take at any point in this plane, we can take moment at this point also, we can take moment at this point also, we can take summation of moment at this point also. So anywhere in this plane, the summation of moments about z direction is 0. Okay. So first we'll apply these three equilibrium equations to the whole truss and calculate these external support reactions. So in our analysis, what we are doing is calculation of unknown forces. In those unknown forces, external support reactions also we have to calculate. Hence, first what we do is, let us say it is a step 1, a calculation of support reactions. So the first step is what? We have to calculate the external support reactions first. Otherwise, it will be very difficult for us to analyze any joint and calculate the member forces, because as we have seen earlier, at every joint if we take, we have more than two unknowns and we have only two equilibrium equations. So analysis will be difficult. So that is why what we do is we'll calculate first the support reactions, and then at each joint we apply equilibrium equations, and then at the end we'll get all the unknown forces, unknown member forces. So first calculate the support reactions. So sigma fx equals to 0. Let us see sigma fx equals to 0. What does it mean physically? It means the summation of the forces that are acting along the horizontal direction, that is our x direction, is 0. The summation of forces that are acting along the horizontal direction is 0. Here we have to take a sign convention, because some forces may act rightwards, some forces may act leftwards. So what we are taking, the sign convention that we are following generally is the forces that are acting in the positive x direction is positive, and the forces that are acting in the negative x direction is negative. And similarly, if we consider y direction, the forces that are acting along the positive y direction is positive, the forces that are acting along the negative y direction is negative. So simply, if I want to say it diagrammatically, the forces acting upwards are positive, the forces acting rightwards are positive, the forces acting downwards is negative, the forces acting leftwards is negative. So positive x direction positive, positive y direction positive, positive negative x direction negative, and negative y direction negative. So in short, we can simply remember it as upward forces and rightward forces are positive, and leftward and downward forces are negative. So let us apply sigma fx equals to 0 first. So let us see the horizontal forces. We have this HA. that is acting rightwards. So we take plus. Now, do we have any other forces acting in the horizontal direction? No. So our sigma fx equals to plus HA, but equilibrium condition is sigma fx equals to 0. So HA equals to 0 implies my support reaction HA is 0. Then sigma Fy, let us calculate sigma Fy, means summation of forces in vertical direction. Now if I observe here, I have force here VA acting vertically upward, I have force here VE acting vertically upward, and again I have force P external. This is external load, these are external support reactions. So I have an external load P acting downward. So downward is negative. So what I will do is, so plus VA plus VE and minus P. So this is my sigma Fy, but as per equilibrium condition, so sigma Fy is 0. So what I will get is VA plus VA plus VE equals to P. VA plus VE equals to P. Now let us see this. This is mathematical form. Let us feel the truss and understand these two steps directly. If we observe this truss, are there any horizontal forces? No. So there will be no development of horizontal reaction. That is the physically we should understand. So HA is directly 0. This will not be there. So horizontal reaction will not be there physically. So HA is 0. Now if we observe vertical direction, we have two forces acting upward and one force P that is acting downward. So for equilibrium, for balancing in y direction, this VA and VE should balance this P. So VA plus VE should be equals to P. So should be equal to P. So like that we have to directly write the equation. So instead of doing mathematically, we can directly observe the truss and directly write these two equations. So that is our step 1. So again we have one more equation, sigma mz equals 0. Now I have to take, sir, you have mentioned at any point in the plane of truss. So at which point we have to select? We have to select the point in such a way that maximum number of forces pass through that point. Sir, why? So let us see the calculation, then we will understand. So I am taking summation of moments about the z direction at point A. I am calculating. So if I calculate here, VA into perpendicular distance is 0. Moment is force into perpendicular distance. So VA into 0. So VA into 0. So anyhow 0. Again when we are talking about sign convention for moments. So we have talked about sign convention for forces. So rightward forces positive, upward forces positive. Similarly, for moment also we need to take sign convention. What I am taking is, so I'll assume that clockwise moments are positive and anti-clockwise moments are negative. So the clockwise moments are positive and the anti-clockwise moments are negative. So please remember this sign convention. So clockwise moments are positive, and anti-clockwise moments are negative. Clockwise moments are positive I am taking, and anti-clockwise moments negative I am taking. Now VA into 0, it is 0, whether it is positive or negative doesn't matter. So again HA into perpendicular distance is 0, because HA is passing through this point, the perpendicular distance is 0. VA is passing through this point, the perpendicular distance is 0. So calculation has become easier. HA into 0. So anyhow HA is 0. No need to discuss about HA. So it will be in simple 0 into 0, because HA is 0. In simple we can say, or simply we can write HA into 0 only for better understanding. So HA into 0. Again, what are the forces there? This P is there. This P will cause a moment of P into perpendicular distance is L. It is mentioned in the problem. So P into L is PL. So moment is PL. Force into perpendicular distance is L. Now this P is causing a moment of a clockwise moment. So let us say I have this point A. Now P is acting somewhere here. If you observe, this is rotating in clockwise direction. So I'll take it as plus PL because it is clockwise moment. Similarly, I have VE here. So VE into perpendicular distance is 2L. This is also L and this is also L. So VE into 2L. Now this VE is causing an anti-clockwise moment at point A. So this will rotate the truss in anti-clockwise direction. So that is negative. So this is my sigma mz at A equals to, so VA into 0, HA into 0 plus PL minus VE into 2L. So this is equals to 0 as per equilibrium. So this is 0 and this is 0. So here PL minus 2L into VE equals to 0. So PL equals to 2L into VE. So L and L gets cancelled. So VE equals to P by 2. So let us say this is 1 and this is 2 and this is 3. So we have got this support reaction, that is HA equals to 0. Now again we have got this VA equals to P by 2. So we know that VA and VE equals to P. So if VA is P by 2, then VE is P by 2, then VA is also equals to, so VE equals to P by 2 and VA plus VE equals to P implies VA is also equals to P by 2. So we have calculated the support reactions. So what is our HA is 0, VA equals to VE equals to P by 2. This is the step 1. This is the step 1. So let us draw some conclusions from this task here. Again, as I mentioned, we have to calculate these things and I understand the loading, understand the symmetricity, all these things, and sometimes you have to calculate directly. So let us see and observe the truss first. So if you see here, there are no horizontal reactions. It means there will be no reaction developed in the horizontal direction. So HA is 0. So again, if you observe, this P is acting symmetrically. So it is acting at a distance of L from the left support and at a distance of L from the right support. It means this P is equally distributed or equally resisted by these two support reactions. So directly we can say that VA and VE are equal and equals to P by 2. They share this load P equally because of the symmetricity, we can say that. So VA and VE are P by 2. So directly we can say, instead of doing all this calculation, we should be able to directly say the support reactions as 0, P by 2 comma P by 2. So let us start the analysis now. Let us start the analysis. So analysis procedure. Now what we do? So we'll start at any joint, we'll apply equilibrium equations at each joint, we'll keep calculating all the member forces, because now we have already calculated the support reactions. The only thing that is left is unknown member forces. So for that, what we do is, we individually go to each joint and apply equilibrium equations and calculate the unknown forces. So again, we have to start at that joint where only two number of unknown forces are present, because if we have more than two unknown forces, we will not be able to, equilibrium equations are not sufficient as there are only two, so analysis will be difficult. So what I'll do is, I'll select the joint first. So first step is calculation of support reactions. Second step is, we have to see for the joints where only two number of unknown forces are present. Likewise, we'll apply equilibrium equations at each and every joint and calculate all the member forces. So that is the procedure. So first what we'll do is, here if I take this joint, I have one unknown force, 2, and this is not an unknown force now, we have already calculated. So I have two unknowns and I have two equilibrium equations. So I'll start from this joint. So this joint is E. So what I'll do is, I'll apply the free body diagram of joint E and apply equilibrium conditions. So let us draw the equilibrium. Let us draw the free body diagram. So FBD. FBD of joint, what is the joint? Joint E. So what I will do is, I will apply the free body diagram of the joint E. As I mentioned while I am discussing about the prerequisites, so free body diagram application is must to understand this concept. So what I will do, so free body diagram I have already discussed roughly. So free body diagram means, we have to represent the forces acting on the body. Now if I take joint E, now if I see here, I have a member force here, I have a support reaction here. So this is acting vertically upward. So I have to represent at the joint, I have a support reaction that is in vertically upward reaction, that is VE. Then again, I have a member force here, I have a member force here. So this is an axial force. So obviously either it could be tension or it could be a compression. So the basic sign convention that follow is, if the force is away from the joint, so if we represent the force away from the joint, then we consider it as tension. If we represent the force towards the joint, then we consider it as compression. So we don't know right now the member whether it is carrying tension or compression at the beginning. So what we'll do is, in the entire analysis, we assume that all the members are carrying tension, and hence in the free body diagram we represent the force away from the joint. So I have a member force here. It is my assumption that this member is carrying tension, and hence I am representing it away from the joint. So a force, this joint, and again I have a member force in the vertical direction. So I have a member force in this member also. So that also I am assuming it to be a tension. So this is the free body diagram of the joint E. So let us name it. So this is DE and this is CE. CE and DE. So this is force in member CE, this is force in member DE. Okay. Now our free body diagram of joint E is completed. Now what is left? Applying the equilibrium conditions for joint E and calculation of these unknown member forces. So only, as I have clearly mentioned many times, at the joint there will be no resistance to movement, and hence only we have two equilibrium equations, that is sigma fx is 0 and sigma fy is 0. So if I apply sigma fx equals to 0, so what are the forces in the horizontal direction? FDE. So it is in negative x direction, so it is minus. So this is my sigma fx, which is equals to 0, implies FDE is 0. What does this mean? It means the member DE is carrying no force. The force acting in the member DE is 0. That is one conclusion. So FDE is 0. Now if you apply sigma Fy equals to 0, so I have in the vertical direction positive, upward direction, that is positive y direction, I have two forces. One is VE, that is a positive upward positive y axis, so it is positive, and again positive y axis, this is positive. FCE equals to 0. So it means FCE equals to minus VE, which is equals to minus P by 2. Minus P by 2. So what does this minus represents? What does this minus represents? Minus represents it is a compression. We assumed that the force is tension and we got a negative value. It means the assumed direction is wrong, and hence it just means FCE equals to P by 2 compression. That is what it means. So we have calculated the forces in this member and in this member. This member is 0 member, and this member I have got is as P by 2 compression. So again I have if I go to this joint, I have two unknowns here. If I go to this joint, I have 1, 2, 3 unknowns here. If I go to this joint, I have 1, 2 and 3 unknowns here. If I go to this joint, I have 2 unknowns here. So what I'll do is, I'll go to joint A and draw the free body diagram of joint A and calculate these two member forces. So let us draw the free body diagram of joint A. So I have HA and VA. I have two forces, let it be theta. So I have HA is 0 here, so I am not representing HA. So let us say HA, and then I have VA, which is P by 2 positive upward. Then I have member in this direction, I have force in this direction also. So this is FAB, FAD. This is FAB, this is FAD, this is angle theta. Now let us see what is this angle theta. So if I say tan theta is L by 2L. So tan theta is, so if I calculate tan theta, it is L by 2L, it is 1 by 2. Now if I say cos theta and sin theta, so tan theta is 1 by 2, cos theta will be, will be root 5. So 4 plus 1, 5, root 5. So cos theta will be 2 by root 5. Sin theta will be 1 by root 5. Now let us resolve this force FAB and then apply the equilibrium equations. HA, I have VA. So again I will be having FAB sin theta. So when we are resolving this force, So this will be, in this direction it will be FAB cos theta, in this direction it will be FAB sin theta. So simply you assume that these things are already you might have already dealt in engineering mechanics. I'm not going to in detail about these things. So in simple, you remember this is, if the whichever side it is close to theta, that will be cos theta, whichever side it is away from the theta, that is sin theta. So this is FAB sin theta, this will be FAB cos theta. So this resolution is over, and again we have FAD here. Anything else? FVA, FAB sin theta. So all the things are represented. A free body diagram for joint A is done. Now let us apply equilibrium equations and calculate the member forces. Sigma Fx equals to 0. So FAB cos theta means FAB cos theta plus HA, all are in positive x direction. So I am taking them as positive. Then FAD equals to 0. So this is already 0. We don't know FAD, we don't know FAB also. So let us keep this equation as it is. FAB cos theta plus FAD equals to 0. Let us keep this as it is. Let us apply sigma Fi equals to 0. So if you apply sigma Fi equals to 0, FAB sin theta plus VA equals 0. Both are in positive y direction, so both are positive. So FAB equals to minus VA by sin theta. Here I am directly writing direct step. So VA is P by 2. So it is sin theta. Sin theta is 1 by root 5. So 1 by sin theta is root 5. So minus. So FAB equals to minus root 5 by 2 P. Again, if I observe, I'll got a negative value. It means FAB equals to root 5 by 2 P compression. Now from this equation, I don't FAB, then I'll get FAD. So FAB is minus root 5 by 2 P, cos theta is root 2 by root 5 plus FAD, which is 0. So if I from this equation and from this equation, I see FAB is minus root 5 by 2 P, and then cos theta is 2 by root 5, then plus FAD equals 0. So 2 gets cancelled, 5 gets cancelled, and minus 1 plus minus P plus FAD equals to 0. So from this, P equals to FAD. We got a positive value, means this is tension. So this is tension. So if we go back, so we calculated this value as FAD is P, this is P, root 5 by 2 P, this is root 5 by 2 P compression. So this is tension, that is compression, this is 0 force. Now these two we have calculated, and the leftover forces is these two. So likewise, we can apply equilibrium equations at all the joints. And calculate the member forces on all the members. So this is the analysis. So what is it? We have to calculate the unknown forces. The unknown forces which are external support reactions and the internal member forces. External support reactions we have calculated by applying the equilibrium conditions to the truss as a whole. So external support reactions are calculated. Then internal member forces we have calculated using equilibrium equations at every joint, and while applying the equilibrium equation at the joint also, we have selected the joint in such a way that only two unknown forces are present. So we'll go to each and every joint, we draw the free body diagram by representing the forces acting on the joint, and then we'll apply equilibrium equations, two equilibrium equations, sigma fx and sigma fy. Then we'll calculate all the member forces. So if you observe, this procedure as a whole is very lengthy. So we have to calculate, we have to go to each and every joint, we have to apply equilibrium equations at each and every joint and calculate all the member forces. Let us see this problem in a competitive exam point of view, because where will be time limited. So let us see this problem. So in the competitive exams, they will not ask you to calculate, find the member forces in all the problems. Let us say he asked me to calculate the member forces in this truss, in this member, in this member, and in this member. Member 1, member 2, member 3. So what I will do is, I will directly apply equilibrium equations at this joint, because I will get two member forces directly. And again, if you observe, there will be options will be available. So let us say member force in one is P by 2 P, and member force in 2 is P, and member force in 3 is P by 2. Similarly, second option, let us take option, this is P and this is P. So second member 0, third member 0, second member P, third member 0, P by 2 0. Let us see this question. He asked us to calculate the member forces in member and giving the naming as member 1, member 2 and member 3, and gave some options. What will do this in a competitive exam point of view? So first we will apply the equilibrium equations at this joint, so that directly we will get the member forces in 2 and 3. So if I observe equilibrium equation at this point, I will directly get sigma fx equals 0 if I apply. So this member force will be 0. So I will see where at 2 only one option I have left. For member 2 only I have one option, so I can directly select this option. Sir, what if I have more than 2 options? What if I have more than 2 options? Let us say here also I have. Then we cannot say whether this option is correct or this option is correct. So we have to go for another member also. So if I apply sigma fx equals to 0, then VE equals to FCE. So member 3 is P by 2. Member 3 is P by 2. If we observe only in this option, so what I'll do is I'll make this P. Now in member 3 only in this option I have P by 2. Likewise we can select, we can solve in a competitive exam point of view. So in a competitive exam point of view, how we have to solve? Directly we have to say that HA is 0 and VA and VE are P by 2 by observing the symmetry. By observing the symmetry, directly we have to calculate, find out the support reactions. In the exam they will give the problems, they will frame the problems in such a way that the problem will be solved in the stipulated time only. So they have given the symmetry, so directly we can say VA and VE are equal and equals to P by 2, and HA is 0 because there is no horizontal support reactions. And if you have to calculate all these 3 member forces, we have to apply equilibrium equations at this joint, and this joint. So means at 3 joints we have to apply equilibrium equations. It will consume a lot of time. So we have to be smart enough to eliminate options and find the correct answer. So with that I'll conclude. There are some more shortcuts so that we, without calculating, without applying the momentic equilibrium equations also, will be able to solve. It will be discussed in the next video. Thank you.